Hey, this is a video response to a video that I saw in my recommended feed recently, about a month ago, from Stormfly about what is the theoretical fastest way that you could complete the Extreme Demon Roulette, assuming you were a perfect player and you could beat any level or get any possible percent on any level on your first try. And so you're like, it's like a robot. Like if you could choose what would be the best 100 levels you could choose for the roulette to complete it as fast as possible. And I was fascinated by this problem. He gave an example of 100 levels. He said it wasn't hyper-optimized, and it was what he believed to be the best solution, but I realized that it was actually, this problem is actually reducible to a well-known problem in computer science called the assignment problem, for which we do know an efficient algorithm for finding a hypothetical solution, of optimizing, of doing everything in the least amount of time, assuming that we knew like the amount of time it would take to get each percent on each level, if that's even possible. I'll touch on that later. So like, if we knew that on Zodiac you could get to 74% in however many seconds, or frames, I guess, if you want to be more precise. I'll use seconds here. And if you could do that with every percent with every level for which that's possible, then you could solve this. So the assignment problem can be stated sort of like this. So let's say we've got 4 workers and we've got 4 jobs we want them to do, and we don't want to assign more than 1 job to each worker. So every worker gets 1 job. Then we can sort of represent that in a 4x4 grid like this, where we have job 1, job 2, job 3, and job 4, and we have worker A, worker B, worker C, and worker D, and we know how long it takes them to complete each job. So like, if we knew that worker B could do job 3 in, say, 7 hours, then we would put a 7 in this square right here, and we would do this for every single square in the grid, right? So we know how long it takes for every single worker to do each job, and we say, okay, we want to select 1 row and 1 column, or excuse me, 1 square in every row and 1 square in every column, so that the total number of time in those, the sum of all the numbers in those squares is minimized. So we might assign job 3 to worker A, and then job 1 to worker B, and then job 2 to worker C, and then job 4 to worker D. And so that's how you would go about solving a problem like this, is using this algorithm, which I'll discuss in a moment. A few differences between this problem and the roulette problem is, number one, for some levels it's actually impossible to get a certain percent. Like many levels you can't die at 99%. There's some levels with long auto sections that obviously you can't die in the middle of an auto section usually. And in those instances we will represent that square by infinity. So like, if we knew that, for example, worker C was physically incapable of doing job number 1, we would just put an infinity in this square. That's not a very good infinity. That's a good infinity. And the algorithm will always avoid assigning job 1 to worker C, assuming that's possible. And we know it's possible since Stormfly has demonstrated that, yes, there exists at least one solution for this problem. The other difference is we actually have more workers than jobs. The jobs are get each percent. Get 1%, get 2%, get 3%, all the way to get 100%. And our workers are the levels. So our levels are Tartarus, the Golden, Zodiac, etc. And we have 150 levels to choose from, but only 100% that we need to get. So we'll actually get a 150 by 100 grid. So the grid is going to be taller than it is wide. And the way that we can compensate for this is just extend it to a 150 by 150 grid, and every extra grid is filled with zeros. So for example, let's say we only, for this classic example, let's say we had 4 workers, A, B, C, and D, and only 3 jobs to assign, 1, 2, and 3. Then we can also model this with just assigning a 4th job, which is just do nothing. And of course, every single square in this column is going to be filled with a 0, since it takes 0 time to do nothing. And we will optimize the sum of the other 3 squares. So that doesn't really change what the optimal solution is. So just to sort of demonstrate how this algorithm works, and by the way, it's called the Kuhn-Munkres algorithm. It's more popular it's more popularly known as the Hungarian algorithm. Apparently people don't really like having to pronounce Hungarian names. But I have chosen 4 levels here, and this is sort of a contrived example. These levels are very deliberately chosen in order to make a point. And I'm going to be using seconds here, is how long it takes to get each percent on each level. So let's say that we're doing sort of a miniature version of the extreme doom in roulette, where we only need to get 4 percentages. We need to get 25%, we need to get 50%, we get 75%, and we need to get 100%. And we've only got 4 levels to choose from, and those levels are, I'm not going to write them all out, we've got Soucoup and Hell, we've got Cataclysm, we have Thanatophobia, and we have the Lost Existence. You can already sort of tell I've chosen these levels to be, because there's something interesting about them. And I've already gone ahead and measured how long it takes to get to each percent. So Soucoup in Hell, it takes 12 seconds to get to 25%. Why is my... Alright. 25 seconds to get to 50%, 38, and then 51 to beat it. For Cataclysm, we've got 17, we've got 34. And that's actually an interesting feature of this problem, is that the numbers are actually increasing as you go down each row, and that's going to be a little bit significant later. But at any rate, this is how many seconds it takes. As you can see, any number of seconds over a minute, I'm just representing by, like 66 seconds is a minute and 6 seconds. The Lost Existences, you might imagine, takes a very long time to get anywhere. So I'll be doing the 4 levels, 4 jobs example. Make that a better... That's 243. So we're going to assume we've got the same number of levels as percents. Of course, if we have 150 levels, 100%, we're going to add 50 rows of zeros at the end. But so what we're going to do here is, okay, what's the best way that we could choose what level we're going to get what percent with? Well, you know, maybe a naive guess would be, you know, let's say that we don't want to have to get very far on the Lost Existence, so we'll choose, you know, we only want to get 25% on that. And you can see, actually, these levels are sorted by, I've sorted them ahead of time by how long it takes to get 100 on them. So the longer levels are near the bottom, so you might say, okay, well, maybe we want to get 50 on this one, 75 on this one, and 100 on the shortest level, Soucoup in Hell. Is that our optimal solution? Looks like a pretty good solution. Is there a better one out there? Well, fortunately, we have an algorithm that can check for us. And so the first thing you do for this algorithm, I'm actually going to copy this so I can paste it later. And now I'm going to drag it over here. And I'm going to recreate this chart here. I'm not going to draw the label of the names and the numbers, but you can just remember which level goes where. So the first thing we do here is, can we assign, can we choose a square in every row and every column so that all the squares have zeros in them? No, we cannot. In fact, there are no zeros in the grid at all. So the first step is, from each row, subtract the smallest number in that row. And incidentally, because we're working with Geometry Dash levels, of course, it's going to take less time to get to 25 than to anything else. So the lowest number is always going to be in the first column, but with a regular assignment problem, like with workers and jobs, of course, that's not always going to be the case, but it is here. So this becomes a 0. We're going to subtract 12 from every single entry in the top row. This becomes a 13, this becomes a 26, this becomes a 39. No, I'm not doing this all in my head. I've got the numbers already written down here. We subtract 17 from every entry in the second row. So we have 0, 17, 39, 62. Subtract 27 from everything in the third row, like this. And then 88 from everything in the last row. And I'll sort of give a proof later, although, well, not really a proof, but sort of an appeal to intuition as to why doing each of these steps is not going to alter the accuracy of our solution. So we've done this. Is it possible to choose a 0 in every single row in every column? So there's 1 0 in each row in each column. No, there's not. Again, all the zeros are in the first column. So what we now do is we say, okay, we are going to subtract from every column the smallest number in that column. So I'm going to repeat this, and the smallest number in the first column is 0, so that column remains unchanged. The smallest number in the second column is 13, so we subtract 13 from every single number in the second column, like this. The smallest number in the second row, or the third row rather, is 26, so we subtract 26, and this process is designed to put a 0 in every row and put a 0 in every column. We're going to get 13 here and 129. Last row, subtract 39 from everything, so we get this going on. That's 203. Okay. So now we ask the question again, is it possible to put to select 1 0 from every row and every column, so every row and column is used once? It's still not possible. What is the most number of zeros that we could assign? Well, we can assign 2, and it doesn't really matter which 2 we assign, so without loss of generality, I'm going to assign this one and this one. So we can't assign 4. If we choose any more, they're going to overlap either in a row or in a column. So what we do here is, our next question is, what is the minimum number of lines that we can draw horizontally or vertically that cover every 0? And there is an algorithm to determine this. It's not a particularly interesting one, but it's quite obvious to see, at least for this small example, that we need 2 lines to cover all the zeros, like this. So once we've done that, well, first I'm going to draw another grid. And the next step is to now find the smallest number that has not yet been crossed out, and that is the 4 right here. And what we do with this 4 is we're going to subtract it from every number that is not covered. So of course 4 minus 4 is 0, 10 minus 4 is 6, 64 minus 4 is 60, 13 minus 4 is 9, 13 minus 4 is still 9, 129, you keep going like this, and you get every single number that is not covered. Did I get all these numbers right? I did. And so now we take that 4 and we add it to every number that is crossed through twice, both horizontally and vertically. Of course, the only number for which that's the case is the 0 in the top left. It's being crossed by the horizontal line and by the vertical line, so we add 4 to 0 and we get 4. And then everything that's only crossed out once, we're not going to do anything there. We're going to keep that the same. And we repeat this procedure. Is it possible now to select a 0 in every row and column? We're getting closer. We've actually got 3 zeros that we can select that don't overlap with each other, but as you can see, that's the best we can do. We can't select all 4. We can't select 4 zeros so that all are in different rows and columns. And so we repeat this step again. How many lines do we need to cover all of these zeros? It actually turns out we need 3 lines. 1, 2, 3. It's not possible to do it in 2 lines. You need 3 for this step. And so we repeat this step again. We go, what is the smallest number that has not been covered yet? It's the 6 right here. So we're going to subtract a 6 from every uncovered number. 6 minus 6 is 0. This math is all addition and subtraction. This 9 minus 6 is 3. 12 minus 6 is 6. 60 minus 6 is 54. 125 minus 6 is 119. 199 minus 6 is 193. And now we add 6 to every number that is crossed out twice, both horizontally and vertically. The only 2 numbers for which that's the case are the 4 in the top left and the 0 right below it. So we add 6 to both of those. 6 plus 4 is 10. 0 plus 6 is 6. Everything else remains unchanged. 0, 9, 19, 0, 0, 0. Is it possible now to select a 0 in every row and column. It's not quite possible yet. We still have just 3 zeros. It's not yet possible to select 4 zeros in 8 different rows and columns. This is actually going to be the last time we'll have to do this. How many lines do we need to cross all the zeros out? Again, it's 3. So we rebuild this grid. What is the smallest number that is not covered? It's this 3, so subtract 3 from every uncovered element. So this is going to stay a 0. This will be 6, 16, 3, 190, 116, and then add it to every number that has not been covered, or excuse me, that is covered by 2 lines, both horizontal and vertical. That's just this 10 here, which becomes a 13, and this 0, which becomes a 3. Everything else stays the same. And finally, we have reached a situation where we can select 1 0 from every row and every column. Yay! And those are these zeros here. As you can see, these are all in different rows and different columns. And you can see that in order to cover all these zeros, we would need 4 lines. And once we've reached 4, then we're done. So this is actually the optimal solution to our problem, is we assign, if I, let me move this down here, and I'm going to paste this, select this, I'll bring this up a little bit, there we go. So we sort of look at this chart and say, okay, well, we've selected the 4th element in the first row, so Sakupenhel is going to be assigned to get 100%. Cataclysm is actually going to be assigned to 50%, which takes it 34 seconds. I'm sorry. Thanatophobia is going to get 75%. Lost existence is 25%. It's not quite what we had thought, which we thought the optimal solution would be this, 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 and this. But actually, you can see the 88s are the same, the 51s are the same, but the 50 and the 56 add to 116, or 106. I'm sorry, I can't do arithmetic in my head. But for the solution we found using this method, the 34 and the 66 add to 100. So we actually save 6 seconds doing it like this. And the reason that this happens, again, I've chosen these examples for a very particular reason, is that Cataclysm is actually very fast in the beginning, and at the end it slows down. It doesn't take very long to get from 0 to 50. It takes a really long time to get from 50 to 100. With Thanatophobia, it's the opposite, and so it takes a very long time to get to 50%, but the second half of the level is very fast-paced, and so it doesn't take long at all to get to 100. And so you can sort of intuitively see why this is the case, because even though Thanatophobia as a whole is longer than Cataclysm, it's worth it to go for 75 on that and only 50 on Cataclysm, just because it takes so long to get to 75 on Thanatophobia, and not very long at all to get to 50 on Cataclysm. So that is how the algorithm works. Here's why the algorithm works and that it doesn't mess up the solution. So I'm going to get rid of this for one moment. Suppose that we have a blank grid. Remember what the first thing that we did was, is we said, okay, well, look at every row and find the smallest element in it and subtract that number from everything in that row. So let's say that we're looking at the first row and the smallest element was 3. So we subtract 3 from this square, subtract 3 from this square, subtract 3 from this square, subtract 3 from this square. Whatever the optimal solution is for the original problem is still going to be the same as the optimal solution for this problem, where we've changed the values just slightly, and that's because every possible solution is going to use exactly one and only one square in the top row. So one solution might look like this, for example. Of course, the cost of this solution is being decreased by 3, but the cost of every solution is being decreased by 3. This this potential solution as well is being decreased by 3. Every single solution is having its cost decreased by 3. And so the relative order of these costs is not going to change. Whatever the best assignment is for the original problem is still going to be the best assignment for this modified problem. And likewise for columns. If we decide, okay, what's the smallest element in the third column? Maybe it's a 7. Subtract 7, subtract 7, subtract 7, subtract 7. Of course, every single solution is going to use one element from the third column, and so subtracting an element from it is not going to change what the best algorithm is. And so we can chain as many steps like this together as we want. For the part where we find the smallest element and then subtract it from all non-crossed elements and add it to every double-crossed element, it's a bit harder to see why that works, but it does still work. And the reason is because we can sort of process these crosses one at a time. The first thing we do is we assume that every element is uncrossed, and we add some number to it. We don't know what it is. Let's say we're adding x to every square in this grid. It's going to take a while to draw. And because like x is the smallest uncovered number, let's just say, or whatever the number is, it's going to be the same for every square. It doesn't really matter what we call it. I'm just going to call it x. So we're adding x to every single square. And of course, this is fine because this is just the same thing as adding x to every row, and so every solution is going to have its cost increased by x, or excuse me, by 4x. Yes, because it's overlapping 4 squares with the plus x in them. And now what we do is, let's say that the second row is crossed out. So we cross this out, and what does that change? Well, all of the elements in the second row are no longer having the x added to them. So instead of being plus x, it's just going to be 0. They stay the same. So it's sort of like we're subtracting x from every element in this row, which we've already added plus x to, which of course we're still able to do. So let's just do this. Let's say that this is, I'm going to use yellow for this, 0, 0, 0, 0, because we've crossed this out, right? Or I'll cross it out first, just so you can see that it's 0, 0, 0, 0. They're not zeros, I'm sorry. We're 0 as in we're not making any change to them. We're not adding x, we're not subtracting x, we're leaving it alone. Let's say we were to add another line. Let's do a vertical one this time. Let's say here. What that's going to do is, I had this backwards. I thought we were supposed to add an x to every uncovered element. We're supposed to subtract it from every uncolored element. I am extremely sorry about that. I'm going to undo that real quickly. Sorry for the confusion. Minus x, minus x, minus x, minus x. It doesn't actually make a difference, but just for clarity, I'm going to redo this. So first line we draw through, I'm going to use a different colored red. It's sort of a brownish, actually. And then so these all become zeros, of course. 0 as in, again, we're making no change to this row. And let's say we draw a second line here. What that's going to do is we're going to, well, again, now this becomes a 0, this becomes a 0, this becomes a 0. This is actually going to become a plus x. Because we're adding the cost to every double-crossed element, and this element now becomes double-crossed. But as you can see, all we've done to this fourth column is add x to it. Negative x plus x becomes 0 for these 3 elements here, here, and here. But the 0 plus x becomes a plus x, which is what we've done with this element here. And of course, we already have established that we're able to add the same number or subtract the same number from any row or column, and it's going to stay the same. So by chaining as many steps like this together as we want, we preserve whatever the optimal solution is, and when we finally arrive at our answer, which is obviously the optimal solution is to select all zeros if possible, whatever those squares those correspond to in the original problem is a solution for which squares we should select in the original problem. So we're sort of working backwards from, we know that these steps aren't going to change anything, so we can do all these steps, get a solution, and that solution is going to work for the regular problem. In practice, I guess this is mostly theoretical video, because in practice it would take a very long time to actually calculate how long it would take to get every percent on every level, there's only 150,000 possibilities, you know? Not too bad. Yeah, that would take a while. And of course, some are impossible. You would have to look for that as well. I guess all you have to really look for is where to skip speed portals and stuff to see how to actually arrive at each percent. But of course, you can't always die as soon as you get to a percent. Sometimes you can only die at the end of a percent. Like, if you got 13%, you might not be able to die at 13.00. You might have to wait until 13.95, right? And so it might be hard, especially if you're looking for exact number of frames, which is more precise, but I guess it does excite me knowing that a theoretical solution exists, and, well, of course a theoretical solution exists. There's only finitely many solutions, but more so that there's an efficient algorithm for finding that solution, because if we didn't have an algorithm like this, we would have to solve it by brute force, and even though it doesn't seem like it would take too long, if we just had a 10 by 10 grid, that would take, let's say we had a computer that could do 1,000 calculations per second. There are 10 factorial different ways that we could make assignments, and that's 10 times 9 times 8 times 7 times 3 times 2 times 1, and that would take about an hour actually just to do the 10 by 10 case. For the 20 by 20 case, it would take about, what is 20 factorial? 20 factorial, 2 times 10 to the 18th power. So let's see, if there's 1,000 per second, 60 seconds a day, no, 60 seconds per minute, 60 minutes in an hour, 24 hours in a day. Yeah, that's going to take something to the order of like several million years to complete. So, and that's just for 20 by 20, let alone 150 by 150. So this algorithm actually runs in O of n cubed time. The number of operations we have to perform is proportional to the cube of the number of rows that we start with, and of course n is the number of rows. And that's pretty good considering that the amount of data is actually of size n squared, because we have an n by n grid. So yeah, that's how you would solve a problem like this. I hope you found this interesting. Thanks for watching. Bye.